Hi again, we are still looking at electricity, and the previous video just had series circuits. So now we're going to look at parallel circuits and see the differences within those. And so we said that a series circuit only has one path of travel. We looked at a series circuit here. We know they're like old Christmas tree lights. If one path gets broken, then all of the lights stop working. In a parallel circuit, you have multiple paths to travel. It's like newer Christmas lights. One goes out and the rest keep working. So you see a series and a parallel there, and we've already said that most rooms, most buildings are wired in a series because you turn off a switch and that one thing that it's connected to stops working. And so here we see a parallel circuit. So let's look at things again. We've got our battery, we've got our switch. So once we've completed that, we have a connection here going to here. We have a connection here going to here. And so now we can see multiple paths that the current can travel. And we can see that because if I take one out, one still works. Take another one out, it still works. The other one still works. There are multiple paths for it to travel. Once again, thinking about water flow comparing to current, we know that if we had water flowing right here, it would be stronger than when it branched off into these individual little pieces. Okay, so in a series circuit, current was the same everywhere. In a parallel circuit, it's not, because we've got a big amount, a big pipe going here, and then it's going there, and it's going there, and it's branching off, so there's less. Also, if you could compare this to the other, and if you can compare them to each other, they're brighter. And there's not a whole lot of a change of brightness. Really, there's not a change of brightness. Or in an ideal world, there shouldn't be when we change them in and out. Okay, and so that's letting us know that the voltage is more consistent. The voltage stays the same in a parallel circuit. And so we had these comparisons that we were looking at earlier. We knew that in a series, current was the same because there was only one path for it to travel. And so like in a lazy river, everything had to be the same. But in this parallel, we had a big amount, and some of it turns this way and some of it turns this way. And well, when we meet back up, it's all going to be the same. But here in these smaller pieces, there's less current going through. So in a parallel circuit, the current will add together. The total will equal the sum of the individual pieces. The voltage this time will be the same throughout. The resistance is the one that really looks kind of ugly. 1 over the resistance is what adds together. So we're going to look at an example of that first. So I'm looking at number 1A on your sheet, but again, I'm going to draw it because it's too small to show up good here. We have our battery, and we have our different branches. And we have our resistors. And so we have 7 ohms and 5 ohms and 2 ohms. And so the way that we are determining our resistances, our total resistance, 1 over the total resistance is equal to 1 over 7 plus 1 over 5 plus 1 over 2. And so then the best way to deal with this is to get a common denominator. It'd be great if it was the least one, but I'm just going to use 70. I think 70 is the least one, but it's going to be the easiest to deal with. So that's equal, right? And okay, finding equivalent fractions. So doing that, and you could do it in a calculator and not do the fractions in your head, but we end up with 1 over our total resistance equals 59 over 70. Well, still, that's not our total resistance. 1 over the total resistance equals 59 over 70. So what would we need to do to each of those? We'd need to flip them. So the total resistance is equal to 70 over 59. And you could keep it as that, or you could find it as a decimal close by. So 1.19 ohms would be okay to say for the total resistance of this circuit. Okay? Now, we're going to work another of those kind of charts, and this time it's going to be for a parallel one. Okay, and so again, this is telling us that we've got R1, R2, and R3, and that R1 is 10, and R2 is 20, and R3 is 30. And that again, we have a total voltage of 6 volts. And so we're wanting to know some things. We're wanting to know for R1, R2, and R3 and the total. What is the voltage? What is the current? And what is the resistance? So this time, based on our rules, knowing that current has to be different and it's going to add together because it's branching off, and the voltage stayed pretty much the same. It was a consistent brightness there that we were looking at. And so if they've told us that the total voltage is 6, then the voltage in each resistor is 6 volts. Now, we need to find the total resistance first. So we've got 10. So 1 over the total resistance equals 1 over 10 plus 1 over 20 plus 1 over 30. And so maybe these are a little nicer to do our fractions with. And so we're going to have 3 over 30. Well, no, we're going to use 60 to deal with that 20 there. So 6 over 60 and 3 over 60 and 2 over 60. All right. And so 6 plus 3 plus 2 gives us 11 over 60. 1 over my total resistance equals 11 over 60. So I need to flip each one. My total resistance equals 60 over 11. My total resistance equals 60 over 11, or really close to 5.45 would be fine. So our first step is to find the total resistance following the rule that we're told for parallel. Still, V equals IR. And so we know a voltage. A total voltage for the whole thing is 6. We don't know the total current yet, but we do know the total resistance. We're going to use our decimal. Okay? And so we're going to say 6 divided by 5.45, and we get about 1.1 for our current. And what we hope happens when we find each individual thing is that they're going to add up to equal that. That's going to let us know that we did a good job. Now, they told us the resistances for each one. We got 10, 20, and 30. And so now all we have to do is do Ohm's law for each resistor. So our procedure is, we remember our rules. We decide what's the same and what adds together. Parallel voltage is the same. Current adds together. And we know how to deal with our resistance. 1 over each thing. Okay, so now we know the resistance each one and the voltage in each one. So now we'll do Ohm's law individually for each one. And so 6 equals current times its resistance. And so we'll say 6 divided by 10. And so we'll get 0.6 amps is the current here for resistor 1. Our voltage is the same, and this time we're dealing with the second resistor. It has a resistance of 20. And so we're going to say 6 divided by 20, and we're going to get 0.3 for the current going through. So the current going through here is 0.6 amps. And the current flow going through here is 0.3 amps. And that should make sense because there's less resistance here. There is less resistance, so more current should go through. Okay, so always keep that in mind. There is more resistance here than here. So less should go through. In fact, how much less? Well, the resistance was twice as much, so half as less gets through. The numbers make sense. And so then dealing with the 30 ohm resistor, then we're going to say 6 divided by 30. And when we do, we're going to get 0.2 amps. So 0.2 amps is what the least is going through here. And that makes sense. And look, this is 3 times as much as 10. And so there's a third as much getting to go through. And very happily, 0.6 plus 0.3 plus 0.2 equals 1.1 amps. So it's just a bunch of doing Ohm's law. And so the first thing we do is deal with our totals based on the rules. And you can memorize them, but every time I do it, I write series, I write parallel, and I write my resistance stuff. And I know that in series, current has to be the same because it's water flow. It's flow. There is only one path, and so it all has to be the same. Therefore, voltage has to add together, and resistance has to add together. Current was the same here. It's not the same here because it branched off. So voltage was the same. And I remember that the resistance has its weird little thing adding together and so on. So first we deal with the total, and then we do Ohm's law with each individual resistor to see what's going on with it. So series has one path to travel, and parallel has multiple paths to travel. And so the good thing about that is that newer Christmas lights, one bulb goes out, the rest of them keep working. And so they're not as dependent on just one path. And so that's a good thing. And so hopefully that's enough to kind of help you work through some of these Ohm's law and circuit practice sheets. Thanks for watching. Have a great day.